So good morning. Welcome to your fifth class of Applied AI. And this is our third time together, right? Last week, you had experiential or actual collab workshop with Marco, reinforcing the lesson we learned in the more like descriptive part. And today is also a descriptive part of the course, right? Now let's review a little bit. Let me start with a quick review of what we did last time, and I'll show you where we launched today. So let's good morning. Welcome to your fifth class of Applied AI. And this is the third time you are with me. I want to start today by a very brief reminder, right, a review of what we did 2 weeks ago. Gradient descent algorithm, the deeper connect between AI and machine learning, right? So this is actually back to lecture 1. If you recall, I made the case that artificial intelligence, in fact, even human intelligence, right? If you're talking about humanoid intelligence or actual human being, the component that make us recognizably human being, okay, can be grouped into 5 aggregates, five pile of definition. The first basically has to do with physical embodiment, right? And for our class, this is not so much relevant because we're dealing with AI in a sort of like computer interface setting. But certainly for things like robotics, the physical embodiment is very important. But even when we're talking about software AI that we interact with a computer program, we certainly need physical embodiment. That's literally the physical computational substrate. So by which I mean CPU, GPU, and all this operating system, right? So the physical embodiment is part of it. Okay, fine. I made the case that this is also not unique to human being, right? Puppies also have physical embodiment. Fine. Let's move to the next one. Next one is sort of like a sensation, feeling, okay? Feeling with annotation or connotation of positive or negative or neutral, right? Again, this is also not unique to human being. Puppies have pain, right? If you poke it really hard, it yelps because it's painful. If you stroke it softly, it's pleasurable. So there's a feeling, sensing, okay, positive, negative, and neutral, okay? And if you talk about robotics, even think of your Roomba, right? Your robotic vacuum cleaner. If it bumps into a thing, that's bad, okay? That's quote unquote painful for the robotic vacuum cleaner, right? Okay, and then we move on to this thing called cognition or recognition. And this is really I mentioned to you I think from very first lecture about the timeline of AI that start with visual recognition with the cat's experiment, how cat detects vertical line, horizontal line. Eventually that led to neocognitron, which by today's vocabulary with the computer science and architecture and hardware, you would recognize under the rubric of convolutional neural network. So that is about recognizing, right? So recognizing that this is a human and not a human. So in your digital camera, it recognizes there is a face or there isn't a face. But the camera doesn't really recognize whose face that is, okay? Whereas if you're talking about your banking application, it has to recognize your particular face as distinguished from other people's face, right? Again, that's not unique to human being because Animal puppies can recognize object, can recognize their owner, can recognize their friend or foes or everything. Okay, so if you want to develop humanoid AI, convincing humanoid AI, yeah, so you have to cover all those bases: the physical, the sensation, positive, negative, neutral, and the recognition of what is the object, what object recognition, basically, right? Then we get to the fourth aggregate of definition, which is a mental concept formation. So basically, this is something that is markedly different in human. Okay, so I already mentioned that animals can count, right? Basically, but they certainly cannot do algebraic equation. So more abstract representation, a model of reality, right? So they do have a model of reality. For example, if you throw a ball, right, and where the ball is going to lie, that's physics, right? So the ball followed the physical trajectory, and animal absorb that physics. So it's kind of like quote unquote physics aware. That's a modern word for AI. But to actually represent an internal model of how variable X and Y relate to one another. Okay, that's something it's a bit more that's markedly different in human being. And I would argue, and that's why I put this triple arrow here. This is really the ability to, or proclivity to construct or to grasp concept abstraction. Basically is very much a hallmark of human intelligence, right? And the concept itself doesn't have to be correct. It can be wrong. It can be even dangerous, right? It can be even evil, but it is a concept. It's okay. So dogs can bite you, but they don't bite you with an abstract concept of evil or causing harm. Okay, so human beings have more evolved or abstract concept of everything from good to bad. Okay, so it could be good, could be bad, could be intelligent or dumb. The point is there is an abstraction, there's a concept formation. Okay, and that's what we were talking about. Okay, now last week we also said, well, this abstract, and the last one is the consciousness, which is basically saying that anything that's happening mentally has to be basically has to have a conscious grasp, which means a momentary grasp. You think you are multitasking, you are listening to music, driving a car, but actually your mental grasp just kind of like oscillate back and forth between different tasks. So there's a present task that you're doing. So that's the conscious handle on reality that your central processing unit is focused on. Okay, so go back to this concept of mental formation. I made the case that we have this mental formation in our brain. Okay, so that's a biological thing. But if you think about it, it's equivalent to a mathematical concept of a function, right? So when you process your thought or when you answer a question, there's an input, there's a processing, and there's an output. So even though we do it biologically with our biological brain, to do it computationally, we have to have a mathematical model. So I represent everything as a function. Okay, so that's why I spend a lot of time making sure you understand the concept of function. Okay, and function takes input and produces output, right? Now, I made the fine point of distinguish two types of input. Okay, one type of input is really a variable. Okay, so basically X. Okay, the other one, in a way, it's an input, but it's a constant input. It's something that is fixed for that context. In which case, I call that parameter. Okay, so parameter, unlike constant of nature like pi or speed of light in a vacuum, unlike those universal physical concepts, parameters are only constant within a given context. Right, within a given context. I give example that for this class, the constant is we start at 9 o'clock. Okay, so 9 o'clock is a fixed constant, but it's only a constant for this class. For the afternoon class, it's 1 o'clock. Okay. Now, what's important about this is that eventually I led to the idea of of AI as some sort of like computational engine. And in a way, you end up an AI engine. Once you train and everything, it's a function. Okay. Then I distinguish between a variable and parameter. Parameter are basically the constants of the AI engine. It's not a constant at when you create an AI engine. It's once you train it. Okay, so when we talk about GPT 3.5, that has 175 billion parameter. See, they use the word parameter because initially this starts out as 0 or random, basically just random 175 billion numbers, completely random. Okay, but once this ChatGPT has read the internet, basically has been training with a large language corpus, Wikipedia and tweets and whatnot, English language, Thai language, all kinds of language, but mainly English, I guess. Once it has done the training, this 175 model, 175 billion model parameters becomes fixed, right? It takes on a particular value. And when ChatGPT or GPT 3.5 or whatever, when it's launched to the public, those parameters are fixed. Those parameters are fixed, okay? So when you have a discussion with ChatGPT, it is learning from you, but it's actually not learning. It's just actually storing more context. Okay, because the learning has already been done because the 175 billion parameters are already fixed. They're not going to change that just because you have a few minutes of conversation with ChatGPT. Okay, so that's considered trained. So that's why we considered we have this. I walked you through this kind of process of AI engine as a function with random parameters, and then it looks at real data and you give it some sort of objective function like minimizing error or maximizing prediction accuracy, and it sort of like changes the parameter value so that the behavior of that function is exactly what you want, and then you consider it done. It's called training. Okay, and then I mentioned that training go back to the initial challenge of AI. How can you program and how can you train or program an AI to behave or interact with you in a human-like? You could not do it in an if-then sort of way, right? Because it would take infinitely long program of infinitely large set of if-then to program the computer. So for that training process to work, it has to be something that is reasonable, it's doable, and the way they did it, okay, in a very small context like medical screening for COVID, yeah, you can do if then. If the temperature is high and the person cannot taste something, then definitely consider high risk for COVID. Okay, if then works only for a narrow case like that. But for a general AI, for a more realistic AI, you definitely can't program all the if then. So you have to somehow program it with the ability to learn from experience. And so computer scientists got inspired basically from how human being learn, right? And the middle part, well, not the middle part, but some part of the previous lecture, I delineated three modes of learning or paradigms of learning. One is unsupervised learning. That's when you're born with the senses and you start to organize reality around you, associate mom with the feeling of warmth and whatnot. And then once you have the capacity to associate vocabulary, then you start have vocabulary, and then your mom can actually teach you, okay, this is an apple, this is an orange, and blah, 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 with direct feedback. So that's supervised learning, right? And then your behavioral adjustment as you enter kindergarten, you get feedback if you behave well, your friends like you. If you bully your friends and don't share your toys, nobody likes you. That becomes reinforcement learning. Yeah, and I made the case that for this kind of AI application, which is not so much focused on robotics, reinforcement learning will play not so significant a part. Okay. In fact, for my data analytics, I teach data analytics class. The AI is in there, but not reinforcement learning part whatsoever. Okay. So it would be mainly supervised and unsupervised learning, machine learning. So the most basic message is machine learning builds AI. Okay. And how does it build AI? Well, it builds AI in 3 modes. But there are 3 modes of machine learning, but we're going to focus on basically unsupervised and supervised learning. Okay, supervised and supervised learning. Okay, and this is the visual recognition. Okay, and okay, so before I go on, I have a quick demonstration I want to show you. Okay, a quick demonstration that I want to show you that remember whether or not it's unsupervised or supervised learning, right? There is some kind of objective or cost function that the training algorithm is supposed to minimize. It's like going downhill, okay? So if the hill is the cost, the lower the better, right? And you want to go downhill. So you start randomly. So maybe you're not at the top of the hill, but you're certainly not at the bottom. You're just somewhere in a forest, okay? And you want to go downhill. The catch is that you don't know where downhill is. You don't know where the bottom is, okay? All you know is that relative to you, which direction is downward. So you take a small step downward. So that's called descent. And the direction is calculated using calculus. So you use the word gradient. And that's also the same word you use in a Boy Scout, Girl Scout when you look at a topography map and say this has got 10% gradient, this is steep, 20% is even steeper, 30% you definitely need walking stick, right? So you have this thing called gradient descent. So basically that's it. That's why the whole thing is called gradient descent. Now, well, yesterday's session, I didn't mention this, but I'm mentioning to you. Sometimes you would not hear the word gradient descent. You will hear instead the word backpropagation. It's because the parameters that you want to go downhill is kind of like sequential in their appearance. So in order to calculate the gradient or the direction of downhill, okay, like if you're standing right now, right, on a mountain, your gradient is either north, south, east, west. Okay, and you evaluate both north, south, east, west together. So you have the direction of gradient. Well, imagine that the direction of improvement is not instantaneous. You have to sort of like calculate the direction of change for each parameter in a sequential form. And the way the AI engine works, it feeds from the input to a layer of processing all the way to output. And so the parameter is kind of like hidden in a stack, right? So you have an input, you have function, and the parameter is used sequentially. So when you want to adjust the value of the parameter in the direction that minimize error or minimize cost, you have to calculate the gradient. Except you don't calculate at once. You calculate from the output all the way back to input. So that there's this kind of like going backward. And that's why it's called backpropagation. So you can say that backpropagation is a specialized term of gradient descent when applied to this kind of, deep layer learning. Okay, so I just want to get that out there. Okay, right. Now, today, okay, let me just hang the topic out. Today, I'm going to go deeper into what's called predictive AI and how that works relative to generative AI and how do you formulate the problem. And I will actually take you through the example of building, a predictive model, right? But before that, I want to just show you like a demo, okay? I got to do this for the previous section, but I didn't get to do that to you. So this is basically what I mean by taking incremental step, okay? Now, oops. Okay, I just want to randomize some data. Okay, right. Okay, so basically, I just created some data, right? Now, all I want you to see is this. Okay, in this case, right? There is right and wrong, just like, this is apple, this is orange. The right and wrong is, in a sense, trying to fit the line, the linear line here that minimize the distance. So basically, it's the line that fits the best through all the points. Okay, I can define this in several ways. The way I define it is, for a given x, I look at actual y. So let's make this big. For a given x, I look at actual y. Okay. Then I take the distance from that actual y to the model, which is the line, okay? And then I square it so that negative become positive as well. And I add all that up, okay? I add all that. So that is my cost. So the better the line fits through all the points, the minimum, the total sum of square distance, right? So this is kind of like the answer. This is the answer. But this is what you start with, okay? So if you start randomly, certainly you're not going to get the right line, right? The line is going to be huge, okay? It's terrible. It's terrible. So basically, if this is the true line, okay, what do I mean by a true line? What do I mean by a true line? What I mean by a true line is that I assume in this case, X and Y follow a linear pattern. Higher X, higher Y, okay? Higher X, higher Y with some initial intercept. And then everything else is some kind of random noise. So my fitting to a line, by fitting a line, I mean a straight line. Because certainly if you fit a squiggly line, you can hit every point exactly, right? But I don't want that. I don't want to fit every single point. I want to fit a straight line. So basically that is the line that is the best. That's the best. And this is a line that starts randomly, okay? So the concept is that that line here has two parameters, the intercept and the slope. And I have to be able to get to from this line, which is wrong, or initial guess, random, all the way to that. But I can't jump at once. I have to evaluate which direction of movement, okay? Should I increase the slope? Should I lower the slope? Should I increase the intercept? Should I lower the intercept? Okay. And again, these are just two number. So it's a little bit like north, south, east, west, right? There's only two number you can adjust. So what I did was, okay, there is a step called, well, okay. So basically, I want to basically get from here to there. So I have to adjust the two parameter, okay? Right? Now, this is cheating, right? Because I know what the true answer is. So I can kind of like do this. Yeah, okay, I got the right answer. That's the best I can get. Okay, but in reality, the algorithm doesn't see the left-hand side, right? It just see the beginning like this. Okay, and it's somehow going to move this thing around to, play with it and see if can get to do that, right? Okay, now let's do this in an incremental. So this is a function called gradient. Okay, basically you can see the square here. Don't worry about it, but that's that's coefficient beta 0, beta 1, right? So that's my gradient calculator. Well, the idea here is that based on this, okay, okay, I can have a gradient and move in the direction. So now it's not random. Now it's not random. So this is kind of like I made it, okay, so that it starts and it keeps improving, keeps improving until it doesn't improve anymore. Okay. Now you will notice that by the time I've done it 100 times, watch this. Okay. So this is from the beginning. I start with 0, 0. In ChatGPT, they don't start with 0, they start with random. Okay. But I can start with 0. Okay, the second iteration is closer, 4th, 5th, 7th, 8th, 9th, 10th, 11th, 12th. By the time I get to 100 iteration, I get to this slope and this intercept. Now, is it the right one? Actually, not quite. Actually, not quite, right? Not quite. But that's because this is my model. Okay, I create this model And it turns out, funny enough, that this one is a better fit than the quote unquote true answer. So I used this to generate the data, but it turns out that it found a better fit. It found a better fit. So the fit error is even better than the real model. Okay, but that's just because I generated real model from randomness. Okay, so don't worry about it. But the point is that this thing incrementally improves. Okay, so that's called gradient descent. The gradient is the direction of improvement. Descent is because every time you take a small step, you go down in the error function. Okay. And for a deep layer, a neural network that has like stack of parameters, the parameters are not presented at once. It's kind of used sequentially. And so when you want to calculate gradient, you work back from the error down. So that's called back propagation for that reason. Okay, so that's just I want to show you that for the case of unsupervised learning. Okay, so that's something that I wanted to show you at the end of the period. And this, by the way, is basically, this is how virtually this kind of incremental gradient is virtually how modern AI is built. Okay, obviously the technique is a little bit more sophisticated, well, not a little bit more, a lot more sophisticated than this, but that's the concept. The concept is you tune the parameter incrementally until you get as good as you can get. Okay, good. Now I'm gonna shift gear and go to the subject of today. And I'll use, I think I'll skip over to I'll jump over to that screen. Hold on. Thank you. Okay. First of all, I'm going to make a very general statement, not necessarily true and not necessarily the way to think about AI for the next 30 years. Okay, but certainly it's a way to think about AI for the next 5 years. Okay, I'm going to separate AI into two groups. Okay, again, this kind of grouping probably makes sense for the next 5 years. Okay, now we'll talk about AI being intelligence, being human-like, intelligence being tactical, strategic information. We talk about intelligence being clever solution, right? Now I'm going to make another partition, which is more relevant to today, which is to separate AI into two groups. One group I'm going to call predictive. Okay. Now, it's not really a nice term because some of this is not predicting, but I will call it predictive as opposed to generative. Okay. Again, this is not hard and fast because as we will see in 2 weeks' time, even generative has predictive part. Okay. And some of generativity is used in predictive. But the reason I want to make this hard separation right now, okay, is the following. Is the concept of what we value in an AI engine. If our value is that it gives us accurate insight that correspond to reality, whether that reality is your customer basis or that reality is trajectory of drone, whether your reality is financial market. It's some kind of thing that you want to have anticipatory capability. So that's why it's called predictive. It's not predict in the sense that this thing is going to be there, right? But it's predictive in the sense that somehow you're projecting the future. So somehow you, if not in the future, then you sort of like extracting some insight, okay? And there's a value in it. So I'm going to put this word down called the value proposition is, it's somehow get you close to ground truth, okay? I just call it ground truth. That ground truth doesn't have to be universal. It could be the ground truth has to do with how your client behaves, how your customer, how your market is going to react to particular sales campaign. And that can change. But it is the truth right now. It's the truth right now that, you know, this generation respond better to color orange than to color pink. I don't know, okay? So is that universal? No, not really. It can change, right? But right now, the ground truth is young generation prefer orange to pink. Fine, okay, fine. So it's about ground truth that we want, okay? So we value it for that. Generative AI is for creativity. In a way, okay? Not everything in generative AI is about creativity, but you can think of it as, you know, you value it for that. So think of artistic creation. Think of anybody has a sharp eye? I really, you know, I'm a big fan of abstract artist Vasily Kandinsky, right? So I asked AI, in this case, I think it's DALL-E, yeah, DALL-E probably, I think, to sort of like, you know, generate something in the style of Kandinsky, okay, for my textbook. And Marco has got very sharp eye, and he spotted Kandinsky influence right away. Okay, but it's generative because this is not real Kandinsky. This is a quote unquote homage, so to speak. Fine. Now, let me give you a quick demonstration of how things work out differently. Okay, let's think about prediction. Okay, about prediction. Go back to predictions. Okay. Let's say you should agree with me. Let's just agree, okay, that predicting tomorrow weather is easier than predicting weather 10 days from now, okay? Because it's closer, you got more information. Does that make sense? Does that make sense? Okay, fine. Okay, but what if I want to predict the weather 10 days from now? That's my job. I want to predict weather 10 days from now, okay? Two options, okay? Two options. One, because I know that a one-day prediction is accurate, I'll build a one-day prediction. Then I use the output of tomorrow, feedback, and then predict 2 days from now. Use that feedback, predict 3 days. Do this 10 times and get to the 10th day. Okay. The other option is to literally have an input-output data just 10 days apart, right? So input is today and the history, and the output should be 10 days from now. And I ask the computer to learn. It's not going to be as accurate, but it's to the point. Okay, raise your hand if you think the first method is better. Raise your hand. 1, 2, 3. Nope, just that, minority. How many people think that directly predicting 10 days from now is better? Okay, right. Okay, here's a gist of it. If you're talking about prediction, definitely, and this is not guaranteed, but you know, as a good practice, you can almost guarantee that even though 10 days prediction won't be as good as one-day prediction, if your objective is to predict 10 days prediction, you should do that. If you create a model that predict 1 day and keep looping back and forth, that error is going to get so big, right? So let's say you have a 90% accurate 1 day prediction and 60% accurate 10 days prediction. If you use 1 day prediction, which is very accurate, and loop it back and forth, that 10% error is going to compound so much that is going to get much worse than the 60% accuracy you get from direct composition. Okay, does that make sense? Does that make sense? Okay, good, fine. So now think of language model as a prediction. When I ask ChatGPT some sentence and it's giving me 5 words, a sentence, what it's doing is it's predicting the right first word, the right second word, the right third word, fourth word, fifth word, sixth word, seventh word, eighth word, ninth word, right? The problem is that thinking doesn't apply here. For one thing, you don't even know that you're gonna that the response is going to require 10 words. Okay, so somehow the way language works, even though this kind of long-range prediction is supposedly going to be better, you have no choice, so to speak, but to predict 1 word at a time. And so what happened is when ChatGPT gives you 500-word essay, it's not giving you 500 words. It's giving you 1 word, feedback, give another word, feedback, another word. It's actually that sequential, which is kind of amazing. And that's why, you know, there's a technological breakthrough called transformer architecture, which is why, you know, you can do this, but not get stupid or still make sense. Okay. So you should not wonder how is it that ChatGPT can give you a hallucination, can give the wrong answer. You should be surprised that ChatGPT gives you anything that means anything at all, because after all it's doing in a 500-word response is 1 word at a time. Okay, it's quite amazing. It's quite amazing. So that's why when you have this kind of if you don't have a bound on matching reality, this generative process, okay, this looping thing, we'll call it generative because it's actually just giving 1 at a time and use that to bootstrap itself. Okay, so it's not your original sentence that's giving 500 word answer. Your original sentence, your question, only give 1, and then that one gets stacked back and then give 2, stack back, give 3, stack back, give 4, 5, until you get 500. Okay, and until you get to some point where you get what's called a terminal signature. So it say, okay, enough said. Okay, so actually ChatGPT doesn't say I'm going to give a 500-word answer unless you specify it. Okay, most of the time it's going to give you answer and keep generating in the next word until the next word is, I don't want to say anymore, enough said. So that's why this thing is going to be very, very different. Now, question is, well, obviously, if all ChatGPT does is a very clever, imaginative conversation that doesn't appear anywhere close to reality, nobody's going to like it, right? Nobody's going to use it. Well, the point is that within this generative framework, there's actual real content in there, okay? Because the GPT is learning to generate new words, but the generation of the new word is based on the language corpus, and that is, you know, Wikipedia and whatnot. And that's why the fact in Wikipedia is stored, quote unquote, in GPT. Okay, it's not in the T part, by the way. It's in another part that's not in the name. Okay, mostly. Okay, so there is that. So it's generative, but the way it generates a next word has to be consistent with what it sees in a human English language corpus like Wikipedia. So that's why, quote unquote, ChatGPT stores Wikipedia. Okay, quote unquote. Okay, fine. So let's do that. Now, 2 different things I'm going to mention. This thing here, this predictive here, you already know from linear regression. Think about it, right? So you already, human history since Sir Francis Galton, that's what, 200-300 years, right? Yeah. Galton, 500 years? Really? Okay. Human beings have been working successfully with predictive, not AI, but predictive analytics for 500 years. And linear regression, as you know, only has two parameters, okay? One for intercept, one for X. And if you have 2X, X1 and X2, you just add one more coefficient, right? So that's why this thing, we've been working with this for hundreds of years. And we can look at it, how it works, like I show you, right? Because it works even for two parameter case. Now, in an industrial strength AI, right? This may be, I don't know, 50,000 parameter, but it's still small. It's still small. So you can demonstrate, and I will demonstrate how this works. Okay. In fact, I can show you how it's built, within milliseconds. But once you get to here, the number of parameter is totally different order of magnitude. It's 175 billion. Okay. So that's why when we come to, how ChatGPT works, most of the time I'm going to be describing to you and showing you a YouTube video of some animation, and then I'll stop the video and I'll describe what's going on or something like that. Because basically I can't show you on my laptop. Okay. Nobody can. Okay. Right. So that's now this here, I can then. So I'm going to say within the predictive AI world, right? Again, AI is built by machine learning. There are three types of machine learning. So you can think of three types of AI corresponding to how it's learned, okay? So again, AI is built by reinforcement learning. There's AI built by supervised learning, and then AI built by unsupervised learning. Okay, right. So this one we're not going to talk so much, right? Because this is more relevant to okay, more relevant to robotics. Okay, today. So today we don't go generative AI. We go here. Okay, and we're gonna go here, supervised learning. Okay, if we have time, we start unsupervised learning. If not, we'll go to next class, okay, which is a combination of unsupervised learning and a bit about generative AI. Okay? In particular, large language model, ChatGPT, and whatnot. I probably won't be able to spend that much time on it because, like I said, you can't demonstrate it on a laptop. So today we'll go to supervised learning AI. So that means, again, AI that learns from matching actual input with a model output that is closely or that's as close as possible to actual output. So again, supervised learning is I have real X and a real Y. I want to stick X to a function F such that it generates Y bar, Y hat, which is very close to each other. Okay? So that's the name of the game. That's the name of the game, right? That's the name of the game. Okay. Now, I'm going to do a bit of hand drawing, then I'll go back to that. Okay, so maybe I should do this like in the mind map. So now we have supervised learning. So I'm going to call it supervised learning problem, like okay, or sort of like a problem. So the problem is to predict Y. Okay. Now I want to say, what do I mean by Y? Well, obviously Y is mx plus b. That's obvious, right? But now I want to be more general. Okay. So we go to this concept, and I think, I don't know if I covered this in the first class, but if not, here it is. think of y as a number. Okay, y is a number. So output of an AI is a number. Okay, eventually it can be text. Just say y is a number right now. I'm just gonna say y is a number. Just like regression equation, right? Y is literally a number. Okay, but not all numbers are equal. Okay, there's like class system. Okay, the most primitive type of number, I would say, is your student ID. Why? It's discrete. So you don't usually have student ID like 1.7. You just have some number, right? So 5123, that's what, let's just say you're 5123. And you're 5124. Okay. What can you conclude about these two people? That's it. All you can do is two people. Can you say that 5124 is a better student than 5123? No, usually just order of registration, which doesn't really matter anything. Okay. In fact, if you go to a medical hospital and you go to a queue, sometimes because they don't want you to have impatient, so the number of order of a service is completely random. So your sort of like service number is random. So you say, okay, I'm serving 7124. I'm serving 1289. I'm serving 9214. There's no order whatsoever. Okay, it's that thing. So we'll call that naming. So that's nominal, right? Okay, mathematically, this is all you can do. Ask the question. Is it equal? Is it not equal? Okay, so now let's say that I'm grading your behavior. Okay, your behavior, which is kind of like qualitative perception. I like you. You are A student. I don't like you so much. You're a B student. Okay. Now, this is not based on cutting grade. In other words, I'm not taking your exam score and anything above 79 is a C grade. Oh, nothing like that. Okay. I'm just literally evaluating. Okay. It's like a beauty pageant. Okay. So this is Miss Universe. This is first runner up, second runner up. So this number has an order in it. It's ordinal. So it's called ordinal scale. The word for it is scale, because if you think about it, you can read this number of like a ruler, right? So if I list you in an Excel, it's like a ruler with the student ID, but it means nothing. But if I say, this is the best student, this is a second best student, this is a third best student, or this is an A grade student, this is a B behavior, okay? What can I do? I can do this, right? I can do this. Oh, okay. Certainly you can hear it that from there. This you can do, okay? So I can say how much, I can say that A is better than B. Can you infer that the distance of A and B, like how much is A better than B? You can't even say that A is better than B by the same amount that B is better than C, right? You can't say Miss Universe is more beautiful than the first runner-up. The same quantity, the first runner-up is more beautiful than the second runner-up. It means nothing. It means nothing, okay? So that's all you can do. Now, notice this thing, these two here, okay? These two here are, in a way, representable with an integer. So, okay? So I'll call it a discrete. Okay. Now, what if I'm talking about, say, temperature of this room? Okay? I can say, yeah, I can say that 27 degrees is 2 degrees higher than 25. So I can subtract, right? So that's called an interval. So I can add and can subtract. Okay? I can add and subtract. Okay? This is really simple. Okay? And ask, Gong Gan, who's like my right hand data scientist way from, when I was working quants at the bank. Okay? These are some of the things that seem simple, but data scientists sometimes get confused. Okay, so interval, I can actually add, subtract. So there's a notion of distance. So this is why you start to use a real number, right? So this is 27.5 degree and 35. Okay, but can I say that a room that's 50%, 50 degree is twice as hot as a room that's 25 degree? Can I say that? No, because that only makes sense for centigrade, right? If you translate it to a Fahrenheit, it's totally different number. So you can't do this kind of ratio. Why? Because there's no absolute zero. Okay, there's no absolute zero. So if you have something that has absolute zero, like for example, your height, yes, you can do that. Somebody who's 1.7 meter and 1.5 is 1.7 divided by 1.5 times as tall, right? So you can divide. So that's called ratio scale. Okay, right? You can multiply even. Okay. Now this thing, most of the time, it's you use continuous number. So I would say continuous. Okay. Right. Those are just numbers. Okay. Now, again, today, AI is all about getting the right Y. Now, I'm just telling you that these are the Ys you can get. Okay. They're Y that means just different. They're Y that means one's better than the other. There's Y that gives a distance of how far between two Ys. And then there's Y that's actually say, oh, this is 0 Y, this is negative Y. Right? So, in terms of problem, I'm running out of room here. In terms of problem, maybe I change the color, if that helps. Okay. In terms of representation, another word that I'm going to introduce, if I can find the pen, is, what did I do with the pen? Oh, there it is. It's all black. Okay. These are good for problem where you are concerned with categorical prediction. Whereas these are good for problem where you can actually want real number, numerical prediction. Okay. Right. Now we start to get back to machine learning, right? So think about these two worlds, categorical, numerical. Okay, discrete, continuous. Okay. So, right? Now let's go back to your regression problem. Okay. Okay. Your regression problem, okay, I'll just draw it. You have a whole bunch of points, okay? And you want to draw a line, okay? You want to draw a line, okay? So that's what? That only works for basically the bottom half problem, right? Because you're giving it a continuous number, right? You give it a continuous number. Now, so actual data would be something like this. So example would be weight and height. That makes sense, right? The heavier you are, maybe the taller you are. Okay, not always. So there's some variation. Okay, but that's basically numerical prediction, right? Numerical prediction. Okay. Not to get you confused, the whole thing is called predictive analytics, but we're gonna call this problem prediction. Okay, predict. Okay, predict. So I'm going to call this problem prediction problem. Problem. Okay. Problem. Okay. Okay. Now let's talk about boy and girl. Okay, boy and girls. I can't write boy and girl. I have to use a number. So I'm just making up the rule. Girl is 0, boy is 1. Okay. Am I saying that boys are better than girls? Anybody thinks that because 1 is bigger than 0? No, nobody does. Nobody in this room does, right? So the only thing you can say is that 1 is not 0 and 0 is not 1. And the fact that boy is 1, girl is 0 is completely arbitrary. So I'm assigning sex to an identity 1, 0, the same way I'm assigning you to 1, 2, 3, 4, 1, 2, 3, 7, right? It's what? It is completely nominal scale, okay? So I put on a scale 0 and 1, I put girls here, boy here. Think of scale as a ruler, okay? Now, let's say, because boys are generally bigger than girls, boys are probably heavier than girls as well, right? What would your data look like? Your data would not look like this, right? Because sex is not a continuous number, okay, in this class anyway, okay? But these are girls. So let me do red for girl. Girl, girl, girl. Maybe there's a girl here, there's a girl here, so that's 0. Okay? There's more girl, 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 girl. Okay? And how about boys? Boys 1. So a little bit short, light boy, heavy boy, heavy boy, heavy boy. Oops, sorry. I should. What I meant to do is this. Okay? There's a lot of boys that are heavier than girls. There's some boys who are light, right? Now, let's think about regression line. Am I going to fit this kind of line? Am I? No, right? So what I'm going to do is fit this kind of line, the line that's sort of like, and then goes like this, right? That's going to be very close. Again, fitting the line is the objective of your predictive AI, okay? The result is a function that takes an input X and gives you a model Y that is close to actual Y. Okay, so I maintain that this line is good for prediction problem. This line is not good for this problem, but this problem, because boys and girls are different class, I'm gonna call it classification problem. Okay, and I'm gonna put big green star here. Any of you have friends who are taking, who are in the med school or in taking biology? Well, in biology, this is not called classification. It's called identification. Classification is when you take animals and separate them into species, right? But when you see one animal and you ask, what species is this thing? It's identification. So if I put all the human in the world and I say, I'm going to separate into boys and girls, that is classification. If I see you and I say, boy, that's actually identification problem, okay? But in AI, which is taking over the world, this is called classification, okay? So don't have a fist fight with your biology friend, okay? So in biology, classification is basically creating distinction, speciation, right? And then you take this animal, what's this? Oh, that's a spotted owl. That's identification, okay? But for us, we say, what's this? This is boy. What's this? This is girl. What's this picture of? Picture of an owl, right? That's called classification. So just keep that in mind. Okay. So which one is a linear function? Okay. The top one's a linear function, right? The bottom one is not a linear function. Actually, technical word is affine because linear function doesn't have intercept. But anyway, ignore me. Now, I'm going to show you something else, right? I'm going to look at this, right? Look at this. I'm going to, okay, assume you understand prediction problem. Okay. First of all, before I go, while I have this picture, can you agree with me that this is the best fit? Okay. What do I mean by that? What I mean by that is that if you have an option of drawing another fit that goes like this. Okay. This is a perfect fit. Perfect fit. But I hope you agree this is a lousy model because that variation is kind of like random. Right? Right? Sometimes there are heavy people who are not tall, or tall people who are not heavy, or whatever, right? So if you fit that, you're not going to generalize very well. Okay? So you agree with me on this, right? Do you have to worry about it? No, don't have to worry about it. Why? Because that red line is not linear, is right? You cannot fit that red line anyway, even if you wanted to. So no harm's done. No harm's done. Keep that in mind. Keep that in mind. Keep that in mind. Likewise, you know, if I ask you, maybe I can fit this one, would you like that? You should say, no, I'm good. I'm good. Okay. That's too much. You fitting, the word is you fitting noise. So it's a random variation. It's not random for the data point because the reason you're big but you're not tall is because you're not tall but you eat a lot, so you're heavy but you're not tall. You're tall but you're not heavy is because you just went to starving or whatever, okay? Or you have a cancer, so you lose a lot of weight. So you're tall but you're skinny. So there's a real reason, but in terms of population, this is completely random, right? You can't generalize basically. So the opposite word of random is basically generalizable truth. Okay. So agree with me that the rates are bad. Okay. Now I'm going to tell you this, keep in mind. If I wanted to draw the red line, it's going to take more parameter. Would you agree? Because the more, just like a line, a straight line only takes two coefficient. If you have a curved line, maybe you take another coefficient for the square term, right? So basically, I can say that in this case, rate is not only just bad, it's also more complicated, okay? So it takes more work to do, okay? But you're not being thanked for it. So, but don't worry. If all you can do is a straight line and a step function, you're not going to end up with the red one. So no harm's done.
What if we reduce the dimension?
Reduce dimension. Can I postpone your answer to that? Because dimension reduction is a very big thing, okay? You're onto something very good, which is, yeah, but no. Okay, let me cover that later, but remind me. Well, you don't have to remind me because dimension reduction is 2 weeks down. Okay, but do remind me. Okay. Here, basically, the short answer is this is basically as reduced as the problem gets. Okay, so this is not working from higher dimension. Okay. Okay. Okay, right. So now, again, your job is to fit the line. Okay, predictive AI is very simple, except it's so good that now that you have this kind of two-way, right? One is like this, and one is a step function. Think of this. Now you can do, okay. Let's say, okay. Let's say this is IQ. Okay, IQ. And you can say this is slug equal to 0. 1 equal to cat or something like that. Maybe 2 is a chimp. And maybe 3 is us, let's say. Okay. Okay. Now it does make sense. Now, technically, you try to measure IQ. It's a kind of numerical scale, but just say humans are more intelligent than monkeys, and monkeys more intelligent than cats. Somehow you want to measure the data, and the data would look a bit like this. Right? With some noise, because there's some really dumb human being and then really smart monkeys, right? So if you think of that step function, in a way, you can also have a multiple step function, right? Right? So what I'm trying to say is that a step function versus not a step function, I'm going to give you a more precise word later. A step function is good because now you can deal with categorical variable, right? Now, in some other problem, you can't stack. So it would be like cats and dogs and chimpanzee, right? But you can't stack one on top of the other. Like it's a good pet. They're all good pet. You can't say cat's better than dog, dog's better than cat. So it's nominal. In this case, it's ordinal. But the point is that once you have this step function, yeah, then you can start dealing with it. So now, with the notion of straight line or something approximately a straight line, continuous line, right? You can have step function. Now, before I go on, I don't want you to get fixated with straight line. What if I do this? Okay. What if I do this? And this is weight. Okay. This is weight. But if this is some kind of health. So it's not monotonic. So maybe there's some kind of like an optimal weight. Okay. Right. Or maybe there's, so this is it's not healthy. This is healthy. This is not healthy, right? What I'm trying to say is that when you work with continuous number, it doesn't have to mean linear. Okay. Another thing is this, right? Anything, any function. The point is that it's continuous here, right? Any value would go. Okay. Just want to keep that. Okay, good. Now, okay, we'll go to the screen. No, we can't. Come back. Yeah. We could either way, but I'm probably quicker with pens. Now watch this, right? Let's go to that old question again. Let's say I have this data point. Okay. Let's say I tell you that the best line is probably something like this. Okay. Something like this. Now, my question is this one a fine or linear function? No. So maybe this one takes how many parameters? Maybe 3 parameters, okay? So maybe this is a nonlinear regression. So you need beta 0 plus beta 1 x plus beta 2 x squared. Okay, right? So sometimes more complicated is better. Okay, the previous picture, categorically, you agree with me, right? If I fit something more weakly, it's no good. So somehow, between this, which has 2 parameters, okay, and this, which has many parameters, somehow you have to sort of like have the middle path, right? Middle way. Not too much parameter that it fits the noise, not too little that it doesn't pick the relationship. In linear regression, when you did linear regression, it's not considered machine learning model because you actually, trust me, you don't actually have to use gradient descent. You actually have a immediate formula for the coefficient. It's like saying, you don't have to take small step downhill. You can actually jump to the bottom of the minimum error. Okay, so trust me on that. I'll show you how it works. But okay, so if you want to go adjust your parameter to minimize error, when you have a lot of parameter and the problem is complex, you have to take small step at a time. But for linear regression, you don't. You actually have a closed form solution that mathematicians have worked out. So it's like saying that I'm standing right here, I jump to the bottom of the hill. Okay, bottom of the valley, whatever. Okay, so technically it's not considered machine learning because you don't have to learn, you just get the right answer. But within the context of predictive engine, it's the same thing. Okay, it's doing prediction work. It's doing y. What's y given x? It's doing the same job basically, right? The difference is this. The difference is this. Okay. When I asked you earlier whether or not the straight line or the weakly line is better, you said the straight line is better. Okay. And what did I say next? I said you couldn't have squiggly line anyway. Right? It's a moot point. So don't worry yourself too much. Right? Because with intercept and slope, you can only fit the straight line. Now, imagine what if I start to open up this, right? And I start to open up more, beta 3, x 3 plus whatever, right? What if I start to open up? I said, it doesn't have to be linear. It can be non-linear. It can have as many coefficients as you want. Now you can get greedy, right? So now this conundrum about enough model sophistication to fit non-linear trend, but not too much that you're fitting individual noisy data point, that becomes a real conundrum. Okay. It's like, if you didn't have a choice of uniform, you go to in high school, you have to have a uniform. You don't have to think so much, right? So you wear uniform, that's it, right? But now you have freedom to wear anything. So is my shirt too long, too short, or the color is too bright or too boring? It starts to become an issue, right? So when you have more freedom, you can have issue. You can literally fit your color to the day. Monday is yellow, Tuesday is pink, right? And you didn't have that problem before because when you were in high school, you have black and white. Monday, Tuesday, Wednesday, Thursday, Friday, same thing. Okay? So something between not wearing the same color every day and literally, every Monday is yellow or whatever. Monday morning is bright yellow. Monday afternoon is dark yellow. So that's a little bit too much. So the more degree of freedom to fit, it's too much. Okay. So that becomes your conundrum. That becomes your conundrum. Okay. So the conundrum is and that conundrum you didn't have when you were studying linear regression because you can't have too many. Okay. So you can have simple. Yeah. And complex. or finely tuned. Okay. If it's too simple, you underfit. Okay. So you should fit this curve, but you use a straight line. Okay. If it's too complicated, overfit. Overfit. You should fit a line that's smooth, but you give it, all the wiggles. Okay. That's not going to generalize well. Okay. I'm going to address just one problem, which is overfit, because underfit can be solved by adding more parameters. Okay. In fact, there's not I think it's a theorem. If you have n data points, okay, you can create polynomial of n degree that fits all the points. So that means you have, n coefficient or something, maybe n plus 1, I'm not quite sure. Okay, something like that. So overfit, in other words, you're fitting noise. Again, when I say noise, I don't mean that there's no personal reason why you should be overweight, underweight, too tall, too short. There's a real reason, but from a probability standpoint, it doesn't generalize well. We call that noise. Okay. Okay. You okay now? Okay. So this is a problem. Okay, it's a problem. And this problem is for numerical prediction and categorical prediction. Okay, both. So, right. So how do you, well, question. So now that you can overfit, let's deal with this problem. Let's deal it in 2 stages. 1, test. In other words, you test whether or not you're overfitting. Okay? If you can do that, maybe you can do 1 step better. Prevent. Okay? Well, it's like disease, right? You want to detect COVID. That's the first thing first is a COVID testing kit, right? Beyond that, it would be better if you can prevent or cure, right? So in this case, we're talking about prevention. Okay, prevent. How do you test? Let's say I have the data set and I fit too much. Chances are when I have a new data set, like tomorrow, the month after, it's going to be worse, right? So in other words, if this is a line, okay, so this is data point, okay, data point, okay, and this is tomorrow's data point. Again, it's not the same, right? It's not the same. It could be something like this. Okay, it's not right. If you fit the right line, okay, you will have some error in the black, but you will have similar error in the red, right? The rate of error will be similar, okay, because the black and red are the same population, just different sample, okay? So if I fit the black line with the blue line, I get some error. Okay. But then I use that line to fit the red line. I'm going to also get similar rate of error. However, if I was too greedy, if I was fitting this line, okay, what happened? The error to the red line will be worse. So in other words, there are two errors. There's error that you measure when you are training the model. And then there's an error for another data set you haven't seen called testing set. If they are similar, then you can say you have an overfit. But if you did so well in the training, in this sample, okay, sometimes called in-sample data, you almost get zero error. But when you go to out-of-sample data that you haven't seen, a testing set, it becomes terrible. This is why beware of, really good prediction that people try to sell you. Okay, I can always show you a perfect stock prediction model. Okay, and then you can trade on it and then you lose money. Okay? It's very easy to do that. It's very easy to do that. Okay, so the idea is very simple. Well, if you have 1,000 data point, let's pretend 10% of it or 20% of it you haven't seen. Okay, in time series, this sometimes makes sense because it's actually sequential order in time. But let's say I have 1,000 students and I want to estimate height as a function of weight, right? And I fit a model. Again, it can be linear, it can be quadratic, it can be complicated. Okay, so I'm not saying what it is. It could be as complicated as I make it. But what's going to stop me? Well, I'm just going to train on 90% or 900 data point and then test it whether or not the same error rate prevails for the 100 held out sample. Okay. Okay, so that's testing. That's testing. So let's do that. Let's say 10%. Okay, and I'm gonna call this train. Okay. Problem with testing is that it doesn't prevent you from overfitting. It just tells you that you overfit, right? So it's like you're a chef. You put in salt, you put in chili, you put in whatever, right? And then you give it to your customer, and your customer, that's too salty, right? Yeah, you get your feedback, but by then it's too late, right? Too late. It is salty. Yes, it's tested. It's too salty, but nobody's happy. Same here. If I train and I test, the test will say whether or not you overfit, but it didn't stop you from overfitting, right? So let's do a little sneaky way. How about this? Okay, and I'm just giving you a magic number here. Let's say I make 75%. This is a magic number I use, but you can use other magic number. Okay, this thing is still called test. This thing is still called training. Okay, this thing I'm gonna give it a name validation. And this is how it works. Okay. Remember regression? None of this is an issue, right? So what happened in regression? You use the whole 100% data set, right? And not only that, regression is a one-stop process. You get from no coefficient to all the coefficient in one go. Okay, so there's no stopping. It just boom. Okay. However, in more sophisticated model that has parameters, it's that situation where you're on the hill and you have to take incremental step. How about this? How about I take incremental step and every once in a while, I test, not with the final test, interim test, right? So what's going to happen is my error is going to go down with respect to the 75%, but Once in a while, don't go all the way, don't go crazy, don't take 100 steps, take about 5 steps, and then test it against the 15%. So I'm gonna get similar error. So I go down again, I get less error with respect to 75. At some point, because you are starting to fit the noise in the 75%, when you sneak a peek at the 15%, it's gonna get worse, right? So basically, you're doing this kind of like partial step. Okay, take 5 steps, take a break, check against validation. And if the validation start getting worse, you know you've gone too far. Okay, you know you've gone too far. So what it would look like, and this is completely made up. Remember, regression, 1 step. Back propagation, this is the step. And this is the error. Okay? If I can train from this and it keeps going down, it's going to keep going down, it's going to keep going down, it's going to keep going down. Right? But it's going to overfit. So what happened is, as I am going down, I do the validation test. So it may be similar. And at some point, my question to you is, where should you have stopped? You should have stopped here, right? Does that make sense? Okay, that's beautiful. In reality, you never get this, you always get something like this. Okay, so it's a little bit more difficult to guess when to stop. Okay, so more difficult to guess when to stop, and that's where, you know, data scientists have experience and have techniques and all that. Okay. Okay, but this is a bit hard to demonstrate. So I'm going to demonstrate to you a 2-step, basically testing, train all the way and then test. Okay, so let's take let's take a 5-minute break. We'll come back and we go to the screen.